Hey there everyone, Mr. D here, and this is going to be the last video for Unit 7 dealing with conditional probabilities. In this video we're going to be talking about conditional probability with a Venn diagram. So Venn diagrams, in case we don't know, are diagrams of those overlapping circles. And we're also going to revisit having a two-way table or a contingency table. So let's get into some definition. A Venn diagram consists of overlapping circles. Each circle contains different elements within it. Where the circles overlap shows the elements that the sets have in common. Okay. Now, one thing that this does not mention is Venn diagrams should always be surrounded by a rectangle, and that rectangle is what's called the universal set. And essentially, this rectangle accounts for anything that just doesn't fit into one of these circle categories. Okay? So let's see an example. We have a class of 147 students. 95 taking math, 73 are taking science, 52 are taking both. Now, we've seen this example used before. Now we're going to start using it to get more into conditionals. All right? When we do this, we want to create two overlapping circles. We want to figure out what are the categories that we're talking about here. Well, we're going to have math and we're going to have science. Now, when we fill this out, I'm going to strongly advise starting from the middle and working our way out. So 52 took both. I'm going to put 52 in the middle. Now, 95 students are taking math. 52 of them are already represented here. That means the rest have to be somewhere in the circle, but not in the science portion. So if there's 52 here and I need 95 total, there have to be 43 over here. For science, I need 73 total. Well, I've already got 52 accounted for. There's 21 left over, so those have to move over. Now, I'm expecting 147 students total. If I add these numbers together, it's not going to be 147. If I add these together, I'm going to fall short. So all of the remaining students, we're going to write that number down here in the universal set. So 31. There are 31 students who have not been accounted for. All right. Let's do some math. I want to know, what is the probability of randomly selecting a student who is not taking math? So if they're not taking math, that means it's anyone who's not in this circle. So essentially, I'm looking for anyone outside of that math circle. So there's 21 and 31. Well, that would be 52 students. So 52 out of the total 147, the probability there would be 35.4. Probability of selecting someone taking math but not science. So they're in the math circle but not the science circle. That's just this 43 right here. Written as a probability, we'd throw it over the total and then throw it into our calculators to get it as a percent. And then lastly, people taking neither or neither math nor science. So they don't fit into either one of these circles. You might be thinking, man, that's pretty lucky, huh? Don't have to take math or science. Lucky you. There are 31 kids who fit that description. Out of our total, 147. Calc, percent, boom, done. All right. Onward. In a class, the probability of selecting a male is 0.3. Probability of someone having brown hair is 0.5. Probability of selecting a male with brown hair is 0.2. Now, when they give us these probabilities, written as percentages, I can put those values into the Venn diagram kind of as percentages and assume, we don't know how many kids are in there. I'll just assume, hey, there's 10 or there's 100, something that would be easy to do percentages with. Okay. Now, we could do it with these whole numbers, 30, 50, 20, or 0.3, 0.5, 0.2. It does not matter. We should get the same result regardless. Our two qualifiers are we have male students, and then we have brown hair students. Okay. all total, I need 100% of the population represented in this rectangle. Let's start filling out these circles, starting from the inside out, and then we'll figure out what's left over. In the middle, this represents brown hair males, and I know there's 20%, so 0.2. They're telling me that 30% were males. Now if there's 0.2 here, then this represents 0.1. And brown hair, I've already got 0.2 accounted for, so that means I need 0.3 over here. Now this whole rectangle has to equal out to 100%. I've got 0.1, 0.2 plus 0.3. I'm at 0.6. So 0.4, 40% of the students do not fall into either one of these categories. So they're not male, nor do they have brown hair. All right. Let's go first one. Probability that we select a female. Well, a female would be anyone outside of the male circle. So 0.3, 0.4, that would be 0.7 or 70%. Next, probability of selecting a male given that they have brown hair. So I need the probability of selecting a male with brown hair all over just the probability of selecting a brown hair student. Well, males with brown hair is 0.2. And the total brown hair population was 0.5. Go to our calculator, we'd get 40%. Next, probability of selecting a female given that the person does not have brown hair. So we need the probability of female, and they do not have brown hair. I'll say NBH, not brown hair. All over probability of selecting someone that just does not have brown hair. All right, so to find this out, we need first probability of selecting a female who does not have brown hair. So that is anyone on the outside of both of these circles, because this means they're not male, nor do they have brown hair. So that's 0.4. All over the probability of selecting someone without brown hair. So anything outside of this circle here, the 0.4 and the 0.1, that's 0.5. Straight to the calculator, we would get 80%. Onward we go. Here's an example that's already been filled out. That way we can kind of see an example in the interest of time here. Freezy's ice cream stand is testing out 2 new birthday flavors, birthday cake and dandy cotton candy. They conducted a poll and showed 32 customers liked birthday cake, 58 liked dandy cotton candy, 12 liked both, and 22 liked neither. So we create a Venn diagram. We start from the inside out. So we have 12 people who like both. Then we go to birthday cake. Well, I know that we had 32 total who like birthday cake. We already know 12 are here. The other 20 have to be over here. 58 like the cotton candy flavor. There's already 12 here, so 46 has to be over here. And then 22 like neither. So that tells us how many people don't fit into either one of these categories. That would be our universal set there. So all together, if I were to add all these values up, I would get 100 total people. Once we have that, we can answer the questions that follow. So this one, we were just not given the total number, but we could figure everything out from there. All right. On to two-way tables. We'll go through, I think, 2 examples. Yeah, 2 examples, and then that'll be it. All right, a study of consumer exercising habits, including 300 married people. So we know 300 married people. 200 of whom exercise regularly. Well, they kind of by default give us 100 don't, right? If 200 out of 300 do, then the other 100 don't. There are 150 divorced people, and 100 of them exercise regularly. Same scenario here. There's 150 total. If they give us 100 do, then the other 50 don't. And then we have 100 people who are just never married. So they give us that total there. And they tell us 40 of them exercise. Well, if 40 of them do, the other 60 do not. So within each of these, they kind of give us little tidbits, and we have to fill in the blanks for the missing pieces. So now let's figure out these conditional probabilities here. I want to know, what is the probability of selecting someone who is married given that they exercise regularly? Given that they exercise regularly. Well, if they exercise regularly, that represents 340 people. 200 of those happen to be married folks. So we do 200 over 340. That gives me about 58.8%. Next, the probability that they do not exercise given that they were never married. So we're looking at the never married folks. There's 100 of them. Of that 100, how many of them do not exercise? 60. So that'd be 60 out of 100, 60%. Next, divorced given that they exercise regularly. So the given that they exercise regularly tells me I'm narrowing my focus to these 340 people here. Of them, 100 were divorced, so 100 out of 340. And that's going to give me about 29.4%. And then lastly, married or exercise regularly. So that word or means we're going to have to add things together. So if I look at the married folks, there are 300 of them out of the total 550. And then I look at the exercise regularly crowd. There's 340 of them out of the total 550. But now I run into the issue that if I were to add these up, I'd get 640 over 550, and that doesn't make any sense. And the reason for that is I've double counted these 200 people here because they fell into the married category, but then I also counted them again in that exercise category. So to avoid double counting, I have to subtract away that 200 out of 550. So now we can combine our like terms up top. That would be 440 over 550, which is 80%. All right, last one. There are a total of 96 children, ages 4, 5, and 6. So they just told me a total. 96 total kids. 37 of these kids cannot swim. 37 can't swim. So that tells me also that if 37 of the 96 cannot swim, what percentage can? Well, I just subtract 96 minus 37. 59 can. Then it says 11 4-year-olds cannot swim. So 4-year-olds, 11 of them cannot swim. 21 5-year-olds can. So 21 5-year-olds are able to swim. There are 36-year-olds. 18 can swim. Well, if 18 can, the other 12 cannot. Now here I've got a few missing cells, but I can kind of go through and filling the missing pieces here. Okay, so for instance, the swimming category. I know there's 59 total. There's 18 here, there's 21 here. How many have to go here to total up to 59? Well, I'd just do 59 minus 21, then subtract 18. We would get 20. Well, now I can add straight down for the 40-year-olds. I would get 31 down there. I can go across the can't swim crowd. 11 plus something plus 12 has to be 37. Well, 11 plus 12 is 13. No, 23, sorry. So that means I'm short 14, so there should be a 14 here for the 5-year-olds who cannot swim. That's also going to help me figure out 21 plus 14. If I add straight down, I'd get 35. Now, just as a little double check, it's a good idea to add straight across, write our row and column totals just to make sure we didn't goof. So if I add straight across, 31 plus 35 is 66, plus 30 is 96, 59 plus 37, is 96. Okay. So now let's get the probability that a student can swim. Well, 59 students can swim out of the total 96. We'd go 59 out of 96. Go to your calculator, and you'll get that's about 61.5%. Next, the probability of selecting a 4-year-old who cannot swim. So I want the probability of selecting a 4-year-old and they can't swim over the probability of just they can't swim. Well, the numerator, the 4-year-olds who cannot swim, there's 11 of them out of the 37 non-swimmers. So 11 out of 37. Go to your calculator. You'll get about 29.7%. Next, probability that they can swim given that there are 6-year-olds. I'm only caring about the 6-year-olds. So there are 30 total 6-year-olds, and of them, 18 can swim. So 18 people are both 6-year-olds and they can swim. Out of the 30 total 6-year-olds, we go to our calculator, we get about, actually no, exactly 60%. All right, that does it for this video. You know the drill. If you have any questions, do not hesitate to ask. And as always, good luck, have fun, be safe, roll tide.